In section 2, we introduced ionic compounds and talked a little bit about their structure. Now that we know what an ionic compound is, in section 3, we're going to get as much practice in as we can for naming and writing the chemical formulas for ionic compounds. Remember that ionic compounds are composed of cations and anions. So before we talk about the compounds, let's first talk about how we actually name the ions themselves. Starting with cations. Cations are the positive ions. So for cations, it's very simple. We name them by putting the word ion to the name of the element, and that's it. For example, K plus would be the potassium ion. Aluminum 3 plus would be the aluminum ion. You notice how I don't have to indicate the charge in the name, because we already should know what charge these elements will have. We talked about that already in previous topics. So when I say potassium ion, we should know that it's +1 because it's an alkali metal. When I say the aluminum ion, we should know that it's +3 because it's in group 3A. But transition metals, what about those? Those are the metals that are in that bottom part in groups 3 through 12. If you recall from a previous chemistry course, transition metals, most of them anyways, can have variable charges, meaning they're not always the same. So it wouldn't be enough for me to say, for example, the iron ion, because iron is a transition metal. Iron has a variable charge. It can have various charges, such as +2 and +3. So when you get to a transition metal, we have to add something extra to the ion name. So if I were to name iron with a 2+ charge, I'm going to very similarly name it the iron ion, but right after iron, in parentheses, I'm going to put the charge in Roman numeral. So if it's a +2 charge, I will put Roman numeral 2. So it would be called the iron 2 ion. Versus if it was iron with a +3, I would call that the iron 3 ion. Now, this is the newer way of naming these particular ions. It is good to note that there is an older method that used to be used. Iron 2+ used to be referred to as the ferrous ion, and iron 3+ was called the ferric ion. Indicating the charge would be by the suffix that was on the root of the ion. This still does exist, it's out there, but we won't use it in this course. We'll use the iron 2 and iron 3 designations. But if you're out there on the internet looking at various practice worksheets, perhaps, just be aware that that is there. Also, you might have noticed, this is actually where we get the symbol Fe for iron. What about anions? How do we name those? Well, for anions, we have to do something a little special. We can't just list the name. Instead, we're going to change the ending to the name of the element to IDE. So for example, Br negative is not the bromine ion, but it's the bromide ion. For oxygen, it's not the oxygen ion, it's the oxide ion. Notice it's oxide and not oxygide. That kind of sounds funny. If it's the general rule is if it sounds funny, it's probably not the correct way to say it. Once again though, notice that I don't have to indicate the charge anywhere because anions, we should already know what their charge will be based on what group that they're in. Anions are always going to be negative, so anions will never have Roman numerals. So don't worry about having to do a negative Roman numeral. Now we get to polyatomic ions. So in the previous, we were looking at monatomic ions, meaning one atom. But we're also going to take a look at examples where we have many atom ions. These are ions that hopefully you've been memorizing since topic 1. These are extremely important, and you need to get to a point where you can not only write compounds and name compounds with them, but you should be able to memorize these polyatomic ions. So what is a polyatomic ion? It's an ion that contains multiple elements, that are held together by covalent bonding, but they act as one group, and so we treat them as one thing. And together, they are known as ionic because they possess an overall charge. So let's dissect that a little bit. Let's consider the polyatomic ion, one of the most common ones, NO3 negative. This is called nitrate. But let's take a closer look at what's going on here. We have 1 nitrogen and 3 oxygens that are bonded together, and that's shown in this picture here. What holds the nitrogen together to the 3 oxygens? That's covalent bonding, which we haven't covered yet. We'll look at that in the next section. But that's what holds it all together. But the nitrogen and the 3 oxygens all act as one thing. They won't break apart. And together, the whole thing is a -1. That's where we get the charge from. And that's why this whole group might bond to, let's say, sodium, which has a +1. And that bond there is the ionic bond. We have an image right here designating another example of that. So consider sodium carbonate. Sodium carbonate is 2 sodium atoms that are bonding to the polyatomic ion known as carbonate. The bonds that hold together the sodium, which are the positive ions, to carbonate, which is the -2 ion, that's the ionic bonding. But what holds the actual polyatomic ion together itself? Covalent bonding. So that's what a polyatomic ion is. Like I said, you need to make sure that you have these memorized. Making flashcards is a really good way to do that. A lot of them sound the same and they look very similar, so you want to make sure you can tell the difference. Alright, so let's take a look at some examples of just naming ions. In example 4, we're either going to name or write the following, depending on what it gives us. For the first one, we have CO2+. Notice the O is smaller, so this is not carbon and oxygen. Instead, it's actually cobalt. Now, ask yourself, can we just say cobalt ion, or do we need to put a Roman numeral? Cobalt is a transition metal, so it could have variable charges. This particular cobalt atom, though, is 2+. So I'm going to put cobalt, Roman numeral 2, ion. For phosphide ion, notice the ending IDE. That tells me that it's an anion coming from phosphorus. So, and then what charge would phosphorus have in ion form? Phosphorus is in group 5A, so it has 5 valence electrons, so it would gain 3 electrons to become like a noble gas. So big picture, it would have a -3 charge. Copper 2 ion. So it gives us the name, we have to write the ion formula. Copper is Cu. This Roman numeral 2 tells me that it's a transition metal. This particular one has a +2 charge. Nitrate ion. Notice the ending 8. If you look back on this slide right here, most polyatomic ions, specifically the ones that contain oxygen, all end in 8 or ite. So when you see those endings, that should tell you that you're dealing with a polyatomic ion, particularly one that contains oxygen. So nitrate is NO3 and has a -1 charge. All right, let's go down to the next row. Manganese 4 ion. Be careful, it's manganese, not magnesium. Manganese is capital M, lowercase n. It's a transition metal, so it has to tell me the charge, and it does in Roman numeral. It's 4. +4. The next one is F with a negative. So F is fluorine, but since it's an anion, we're going to change it to fluoride. And then add the word ion. Notice the spelling of fluoride. It's F-L-U-O, not F-L-O-U. Spelling counts when you are working on naming and writing compounds. So please make sure you note that. Alright, next one, Sr2+. This is just an element, a simple cation. Sr is strontium. I don't need to include Roman numerals because strontium is not a transition metal. It's in group 2. It's an alkaline earth metal. Next one is SO4 2-. This is a polyatomic ion. It's going to have a special name, sulfate. And then the last row, CO3 2-. That is carbonate. And like I said, this is where you have to just memorize these polyatomic ions. C2H3O2-. Some students are tempted to get all weird with the namings. Dicarbon, If it starts to get weird, that should indicate, maybe this is a polyatomic ion. And it is. It's acetate. Sulfide ion. Notice the IDE ending, so that tells me it's just the element sulfur. And what charge would sulfur have in ion form? 2-. And then finally, sulfite. Notice the ITE ending. That tells me this is a polyatomic ion, specifically SO3 2-. Now, one helpful hint I'm going to give you on this slide, since it's getting brought up, is that as long as you know the 8 ion, you can actually figure out what the other ones are based on the number of oxygens. Here's what I mean. What's sulfate? Sulfate is SO4 2 minus, right? Sulfate. Well, what if I asked you to write sulfite? The difference between 8 and ite for a particular polyatomic is just one less oxygen, and that's it. So sulfate is SO4 2 minus, sulfite would be SO3 2 minus. What if I asked you to write hyposulfite? So not only is it ite, but now it has hypo in front. That is one less oxygen still. Keep removing oxygens. So that would be SO2 2 minus. And then finally, what if I asked you to write per-sulfate? You have the 8, but you have this prefix per. That means you're going to add an oxygen. SO5 2 minus. So as long as you know the 8, whether that's sulfate, carbonate, acetate, nitrate, you can figure out all the other ions based on that little trick. Just make sure you know that each polyatomic ion is different. For example, sulfate was SO4, but nitrate is NO3. So you need to make sure you memorize the 8 ones and then add or subtract oxygens as you go. So that's a little trick. Alright, so now we're going to start writing formulas. I'm going to teach you two methods. You choose whichever one you want. So when you go to write a formula for an ionic compound, keep in mind that the cation and the anion charges have to equal 0. So what we'll do is we'll add cations and anions until that happens. I'm going to show you two methods, the T-chart method and the crisscross method. So the T-chart method, let's look at that first. Example 5. If I asked you to write the formula for potassium nitride, first of all, I notice that it's an ionic compound because potassium is a metal. So I'm going to use my ionic methods, and this is the T-chart method. Put the cation in one column and the anion in another. Nitride is just nitrogen. Then determine their charges. Potassium is +1, nitride is -3. Now obviously you need at least one of each, otherwise you wouldn't have a compound. So you need at least one potassium and you need at least one nitrogen. So I draw circles to represent each one. And each time I draw a potassium, that has a charge of +1. Each time I draw a nitrogen, that has a charge of -3. Ask yourself, do those charges cancel out to be 0? No. So what do you need more of? You need more positive. What if I added another potassium? Well, that's getting closer. Now we have +2 to -3, but I need to add one more. Now, the +3 cancels out the -3. So then ask yourself, how many potassiums did you need? You needed 3. I write that as a subscript. How many nitrogens did you need? I just needed 1. I don't need to write the subscript 1. I can just write it like that. That would be my formula. The other way you can do it is the crisscross method. A lot of students prefer this one, but you use whichever makes sense to you. The crisscross method is this. Write out your ions. The cation always gets written first. Then write their charges. +1, -3. Now, looking at just the number, not the charge, so not the sign, we are going to crisscross. The 1 from here will be the subscript for nitrogen. The 3 from here will be the subscript for potassium, therefore producing K3N. The only thing you have to watch out for if you do the crisscross method is you have to look at your chart or your subscripts. If they can be reduced, you have to reduce them. 3 and 1 cannot be reduced, and so K3N would be our answer. I do sometimes see students on an exam, they'll do this, and then they'll leave that as their answer. Your answer needs to not include the charges. Either erase them or just rewrite it down below in another spot. We're going to continue on with the other two examples in example 5 in the next video.